Hi, welcome back. It's been a while since I did a video on quantum mechanics and my models, which I call RealQM, Real Quantum Mechanics. So today we're going to map out what I think of as a groundbreaking alternative to standard theory, standard nuclear theory. Let's get on with it. I'll explain these figures, but first, well, what you see here is basically an electron model and then a proton model. You can immediately see that we model the electron as a planar 2D oscillation, charge going around and round and round, 2D ring current, and the proton as a three-dimensional oscillation, a spherical shell of charge. Is this new? No, the ring current model has been there since 1905, I think. Proton 3D models, well, we know there's spherical packing in nucleons, so everybody sort of knows that a proton is not something flat. But the reality is that mainstream physics, the standard model, or I would say modern quantum mechanics since the Second World War, as opposed to old quantum mechanics, the quantum mechanics of Schrödinger, Dirac, Einstein, and Planck. Well, modern physics has actually no theoretical explanation of the proton charge radius, nor of the electron radius. It treats elementary particles as point particles, infinitesimally small particles, basically with zero dimension. So we think of elementary particles as something real, something that occupies some physical space. We also do away with what I would call then phenomenological parameters, and especially with the so-called nuclear or strong force to explain why protons stick together in a nucleon. Everything we do can be explained by electromagnetics, laws of Maxwell, combined with Einstein's mass-energy equivalence relationship. Very important because we will explain mass, how mass emerges, not by a Higgs field or something, but just mass as a inertia basically to a change in the state of motion of oscillating charge. And then the Planck-Einstein quantization law, of course, energy, momentum, linear or angular, or physical action is quantized. So let's now look at the screen. So the electron operates here perfectly, really as a flat 2D ring current. You can go on my ResearchGate page and look up the where I started, explaining the electron radii, the Compton radius, also the Bohr radius in an atom, and the Lorentz or classical electron radius. The proton is much more complex, and it took me years to model it as what I think it is, a three-dimensional spherical shell of charge. In the formula for the radius, and I will also use that to explain the magnetic moment of a proton, there's a factor 4. And that factor 4 emerges really, pops up everywhere, and it really emerges, that's the basic thing you need to remember from, well, that area formula for a 2D ring current. The area, or the circumference, is pi times the square of the radius of the oscillation. For a shell, you have a surface area of 4 times pi times the square of the radius. That factor, I will go to the numbers later, that sort of predicts the proton radius at exactly 0.841 femtometers, which really matches recent empirical proton radius measurements. There has been a lot of progress on the so-called proton puzzle, not so much in terms of building a workable theoretical model, which I think I have, but in terms of really tuning or having a more precise measurement, empirical measurement of the proton radius. Both the Thomas Jefferson PRAD experiment, National Accelerator Facility, JLab, as well as sort of the cooperation between the Max Planck Institute of Quantum Optics, MPQ, and the Paul Scherrer Institute, PSI, which uses basically muonic hydrogen data. Well, our theoretical radius matches those measurements exactly, but we use only pure classical electrodynamics. Yeah, I will refer to the Proton papers and go quite briefly over the math, not very much at all actually, because this presentation, as it's because it's a YouTube video, sorry, presents mainly visuals. This is sort of when we model charge as a three-dimensional oscillation. We have basically two modes of oscillation that are perpendicular to each other. An oscillation in one plane, and it oscillates in the plane that is perpendicular to it. The funny thing is, here you see sort of that trajectory, and the basic difficulty for me, which I solved only after many years and with the help of AI, basically, Gemini, DeepSeek, ChatGPT, we all looked at this. The problem was really to find sort of a frequency ratio, a frequency for the, let's say, the horizontal and then the vertical oscillation, the two planes, which both have a frequency. The frequency ratio that we used is a square root of 2. Why is that? We found it must be the fundamental spatial coupling ratio, because the issue was really how does a single point charge, as we model it here, so we have a point charge going around and around, how can it form a stable three-dimensional sphere? The math tells us that, let's call the two oscillations the polar and the azimuthal planes, well, frequencies. The two planes are marked by these frequencies, omega 1 and omega 2. If the two oscillations would lock into a three-dimensional oscillation, which is marked by two frequencies that are in that relate to each other through a simple integer fraction, 2 or 3 or a half or whatever, then the only stable path that emerges is really a planar ring, a 2D current. Why don't the other paths work? Well, they don't come, well, when you use an integer fraction for the polar and azimuthal frequency, you don't get a constant tangential velocity. What is a tangential velocity? The velocity of the point-like charge. Well, it's light speed. I'll explain that in a moment. And we think, we model here a naked charge. It has no rest mass. The mass that it acquires is a relativistic mass. So it must therefore, if it has no rest mass, really go around and around at speed of light. So, but all 3D paths that we tested, all kind of models and frequency couplings, they didn't come with that constant tangential velocity, and so we thought of them as being unphysical, even if they generated, an okay magnetic moment. That thing didn't come out, the constant velocity constraint, as I call it. So we might say that for the proton, what our model yields, and it's, I said, it predicts all observed quantities, the proton mass or energy, its magnetic moment. We might say the proton is sort of where nature applies an irrational synchronization. The irrational just refers to an irrational fraction, that's square root 2, for the coupling of the two orthogonal oscillations. Why square root 2? What irrational fraction would be used? We can think of square root 3 or whatever. Well, it's actually the most basic of all Euclidean metrics, square root 2, square root 3, square root 5. We might have used others, but this most basic of all Euclidean metrics works remarkably well. What's the point when you visualize it? When you really and I'll come to that. How you go, how you calculate those coordinates in space and time of the motion of that point-like charge. What you see is that actually the point charge never really hits the same coordinate twice. It sweeps out a continuous non-closing in the sense that it doesn't close in one cycle. Current shell that fills the space. It fills a 3D shell. So that's sort of how it looks like. I'll come to that actually. Well, let me first talk a little bit more about that velocity constraint. Oh, well, no, I have another one here. This shows, yeah, this is what I wanted to show. When you looked at the trajectory, you can see that there's a polar concentration. And that's sort of what you see. We project here the motion of the charge on the xy plane and on the xz plane, and you see that sort of near the poles at well, the charge there has a higher density, I would say. It passes, it lingers there, and that's sort of where you know, the charge wraps there into these more dense spirals at the poles. And that sort of creates what I think is also what we see in experiments, a very dense, concentrated structural core. The other graph there is the polar angle, and then sort of the azimuthal angular rate of scaling, as I call it, and the relationship between the two. And you can indeed see that, you know, near the equator, you know, you have a very low coupling and or rate scaling, I would say, and sort of near the poles, you have a very dense one. If you measure strictly the velocity along, if you measure polar and azimuthal velocity, you will see nonlinear accelerations, and that's sort of where the model, we will come back to that, where the energy conservation laws, you know, need a bit of interpretation, I would say. Let me use this thing because this is actually a slide I inserted later, and I did not prepare too much text for it, to reiterate basically. You know, the idea behind this naked charge traveling at light speed. The idea is really this: mass is quite simply inertia to a change in the state of motion of this charged oscillation. Where does that come from? Basically Newtonian mechanics, but relativistically correct Newtonian mechanics, where we have relativistic momentum. And we combine it with Einstein's energy is mc square relation, which basically tells us that mass is unlike what you know, standard theory would tell you, is not some kind of substance, a Higgs field or whatever. It's really what it is: a measure of a system's resistance to a change in its state of motion, its inertia. So what is moving then? It's state of motion. Motion of what? What is moving inside a proton, inside a particle? We call this the naked charge. It's just a charge as it appears in Maxwell's equation. It has no intrinsic rest mass, zero rest mass. It has also no intrinsic spin or other, you know, quantum or non-quantum properties. It's a pure point of charge, and we will later argue that probably, you know, it's not zero-dimensional. But all the physical properties of particles emerge really exclusively from the motion of this charge. So we have here what I call a relativistic mass generation mechanism, because this naked charge is locked into a continuous high frequency oscillation at the speed of light. It acquires relativistic momentum and mass. So it resists external acceleration, not because it contains heavy matter. Matter is energy, but because its internal velocity is maxed out at this cosmic speed limit, this speed of light. So in terms of equations, energy equations, which physicists would like to hear, energy, as you know, is physically defined as a force acting over some distance. In this 3D model, the force is electromagnetic force, electrostatic and electrodynamic, magnetic, electric. And so these internal electromagnetic forces act over the orbital distance of a complete cycle. And that cycle, you will say, okay, you just said that the point charge doesn't return to the same coordinate after a cycle. But that cycle is defined. It's still governed by the Planck-Einstein relationship. The energy is Planck's quantum of action, h, times the frequency. So the rest mass of the particle is simply, the equivalent mass, the inertia of that total energy. That's related to that physical action that is tightly packed, I would say, into these localized, and I'll come back to that, non-radiating spatial oscillation, because that's often, okay, you got something going around here, a charge. It should radiate out its energy. We will explain why that's not the case. So it works fine. I said the thing we've been struggling a bit was that these standard spherical coordinates introduce this angular speed bottleneck, I would say, at the poles. So the radius of the oscillation really sort of shrinks, as you can see here near the top and the bottom. The linear velocity drops, but the azimuthal rotation compensates for that in a nonlinear way. So I'd say problem solved. So here we have a bit of I really messed up my text for the slides, but I'll soldier on. We have that particle at rest, the proton, and we said it. It's sort of like a resting clock, I would say. The phase is like a clock, and that's sort of similar. What standard theory and RealQM have in common. We both think of the phase of the wave function. We will come back to that, how we can describe this in terms of a three-dimensional wave function. But it's sort of the particle clock. What happens if the particle moves? Here we have the reference frame is the reference frame of the particle at rest. The reference frame of the observer and the proton is the same. When we see a moving proton, we get something like what you see in the second figure, a moving Wavepacket, I would say. A linear velocity gets introduced, and then the spherical current, or spherical current, well, yeah, it's spherical current, but you can see it's a complicated one. It stretches into sort of, a very complicated helix, which becomes ellipsoidal, and that's where the famous de Broglie wavelength comes in. It's really that sort of it introduces sort of a phase beat pattern of on top of the invariant clock, sort of a macroscopic phase. So we'll come back to that. We have an invariant anchor. I note that there on the top, the energy is equal to the reduced Planck quantum of action times the omega, written as a capital letter to distinguish it from the omega, not capitalized. the omega 1 and omega 2 that characterize the polar and azimuthal frequency of the two orthogonal oscillations. So at rest, said total mass energy is locked into its global frequency, which we can relate to either the polar or azimuthal frequency, omega 1 or omega 2, because omega 1 and omega 2, the ratio is the square root of 2. We can calculate this capital omega, the global internal frequency, the global clock speed. I would say omega is the square root of 3 of omega 1. Yeah, I read that there this invariant combines. I'll come back to the math of that. The polar and azimuthal modes, the two modes of oscillation, quadratically. I'll explain in a moment what that means. Translational shift, we talked about that when the particle begins to move linearly relative to the observer. The internal 3D spherical envelope starts elongating into an ellipsoidal helix along the axis of translation, which we will introduce that we will label as direction K, using an imaginary unit, Quaternion, like in Quaternion algebra. I have the imaginary unit I, J, and K, which basically you can interpret as rotational operators or the directions of the three axes in three-dimensional space. Yeah, I wrote here some rather highbrow stuff that you can read in my papers. I call once it moves laterally, we may define a propagation operator, K with a little hat on it, which acts on the translation axis. So yes, the rest is the same. We calculate this internal high frequency rotation, the capital omega, as you know, of the order of 10 to the power 24, the underlying clock. And it's sort of, yeah, this clock is like Doppler shifted by linear movement. So that's an explanation of de Bruij's wavelength as a function of the linear momentum p of the particle as a whole. And I said it's sort of a macroscopic phase beat pattern that you have, which in standard theory, the standard model or standard quantum mechanics is also there, but as a sort of a 2D wave function. 2D wave function, sorry. The radiation problem, yeah, what we do have, I will refer to my papers on ResearchGate on that. Why doesn't it radiate its energy out? The key here actually is that the this irrational frequency ratio that we found, and the fact that there is no path repetition, causes the charge to indeed sweep the entire spherical boundary. And the nice result that comes with it is actually that these local fields and the motion sort of never detach as radiation. The local fields that are generated by this motion never quite detach as radiation waves. There's sort of a dynamic feedback that generates forces that continually drive the point charge back along its trajectory. So this potential stress, as I call it, and the kinetic circulation, just like in the electron model, form really a locked equilibrium and explain why this path is first self-sustaining. The forces it generates keep the motion going, and secondly, also why it's not radiating any energy out. So let's go to the predictions, these hard numbers for the proton. For the proton charge radius, as said, there's no theory really. There's models that fit parameters phenomenologically, but in RealQM we have that formula for the charge radius, which I said is 4 times h bar divided by the proton mass times the velocity of light. We can see these as sort of the Compton radius of the proton. It differs from the Compton, the formula differs from the Compton radius of the electron, which is also sort of a real physical radius from photon scattering experiments. But the electron Compton formula doesn't have that factor 4. The empirical value, as said, comes out all right, both in terms of what the PRAT from Jefferson Lab predicts, and these muonic hydrogen experiments from the Planck Institute and the Paul Scherrer Institute. The magnetic moment. Yeah, the magnetic moment of the proton is often called anomalous in itself. We don't think it's anomalous. We get a theoretical magnetic moment that is equal to 2 times the square root of 2 times the nuclear magneton. And so the factor 2 and square root, I will explain that. It's really explained by this form factor, the fact that it's a 3D oscillation and that we have these orthogonal couplings between the two oscillatory planes. That yields the yield value of 2.793 times the nuclear magneton, and that's within 0.54% error. This 0.4% error is not a model failure, not at all. First, it is still within the experimental uncertainty of the measurement of the magnetic moment, and secondly, it's sort of like a physical signature. When you read our papers on the anomaly, the real anomaly that is measured to a very fine degree in experimental physics, we say basically, okay, this is a naked charge, but we do think of it as having some very, very tiny physical space. It takes up some space. For the electron, we have an explanation of the anomaly in the magnetic moment of an electron based on the fact that this size of the naked charge would be of the order of the fine structure constant times the Compton radius. So here will we have the same, we're not sure. The measurements for the proton, because it's so tiny and so massive, haven't come out really with an anomaly, a difference from that empirical value that you see here, 2.793 times the nuclear magneton. So, but we think that will be there, and so actually we think that, as being within the uncertainty of the measurement, but not quite on the center of it, actually indicates that really zero-dimensional mathematical points, they don't exist. The naked charge is still naked charge. It's point-like, but it's not infinitesimally small. Not infinitesimally small in the sense that its radius would be 0. Probably be many, many, many times smaller, or perhaps our ring current model needs to be adapted more as a toroidal model with a certain thickness. But that's what we think. The naked charge probably has a real non-zero physical thickness, and that will probably slightly dampen this ideal theoretical magnetic moment that we calculate here. Particle spin, very abstract in the standard model. It's sort of an intrinsic state. For us, particle spin is it's about physical action. Planck's quantum of action is a certain discrete amount of physical action, and we find in our model, if we integrate the linear momentum along its motion, so it comes from angular momentum, over the trajectory over one cycle, we get an amount of physical action that is equal to h divided by 2. So for us, it's really quantized action, quantized physical action. So particle spin is real for us, and it's fermionic because proton and neutron, or two protons, they they can't go and just sit on top of each other because of the electric magnetic forces that come into play. The mass generation mechanism, we talked about that in standard model approach. You know, there's this deus ex machina. I think of it, the Higgs field coupling with strong force, with a weak force, with whatever, with the electromagnetic field. For us in RealQM, it's kinematics and electromagnetism only. We have this. We have Einstein's mass energy equivalence formula, E is mc square, and so yeah, for us mass emerges naturally, as said, as a measure of the inertia in the state of motion of that moving particle. Empirical value that we get is really 938.27 mega electrovolt, which are right on, of course. Let's move to the neutron. I call this sort of well, the neutron conversion, or conversion from the proton model to the neutron model, and explain why, you know, a free neutron outside of a nucleon will decay. That's what I call the phase mismatch decay, and why inside of a nucleon it doesn't. It enters into sort of a complicated, I will explain that, and the Deuteron, proton and neutron together, where there is sort of the decoherence, as I call it, of the free neutron, becomes a coherent oscillation, and the proton has a coherent oscillation as a free proton, but you know, it becomes a really complicated multi-body problem. But it can be modeled as a stable oscillation of two particles, a neutron and a proton. I won't go into the math of it, but basically our model is sort of based on the fact that the neutron has a magnetic moment, and that magnetic moment that is negative, and not positive like of the proton, but that its net charge is zero. So we think of the neutron as basically not a composite particle; it's an elementary particle, but as being composed of you know, two charges, a negative one and a positive one, that give then that net neutral current, I would say, or net neutral charge of zero. We think of it, and that's a bit unlike, you know, the literature varies a bit on that. The form factor for a neutron will often model a neutron as sort of a positive layer around a negative charge ray. For us, it's just the other way around. We have a positive charged layer inside of a negative current, 3D current, as you can see here, the reddish, and then the what is it, the appelblauw zeegroen, we call it in Dutch. It's sort of that light greenish bluish. In the papers you find on the neutron model, you will see the math that's behind the graphs here, the variational energy landscape. It's a variational model. We apply the principle of least action to calculate again these trajectories, you know, energies, potential energies, kinetic energy, and we find indeed that for you know, the stable equilibrium, the radius ratio of the negative charge, that is oscillation, and the positive charge ratio, R1 over R2 is about 0.569. The normalized radial distance from the center is more or less the same graph. We have that green bluish zone where it is self-sustainable. So it's a normalized radial distance at 1, but between you know, some definite positive radius and the normalized radius of 1. It's the self-sustaining zone where the two charges don't spin away from each other. So to wrap this up, I said standard physics again has no real neutron model. It struggles really. Why? Because of that, why a neutron has that rather massive magnetic moment. I mean, smaller than the proton moment. I think our core shell variational model answered that. But I said the proton is a single unperturbed 3D shell, giving a very clean 2 square root 2 times the nuclear magnetic moment. The neutron combines that inner positive core and an outer negative shell, which interact through, I said, in a free neutron, what is this coherence, structural coherence fraction. I stress that because I use it actually to build up multi-body nuclear models of a nuclei with many nucleons. So outside of the nucleon, the free neutron, there's a phase drift. Cancellation is imperfect. Yields a net negative moment, and yeah, after a while it falls apart into a proton, an electron, and a neutrino, which we think of as sort of the 3D equivalent of a photon. So it's also a 3D oscillation, but of electromagnetic fields. I can go into detail again, the papers, that 3D modelization of a neutrino also explains why neutrinos do appear to have some rest mass, but it's in appearance only. Okay. Next one, we're at 36 minutes already, and we have still a lot of slides to go. This would probably take an hour. So let me go a little bit quicker, the proton-neutron comparison just for the magnetic moment. Just to be clear on, terminology, the Bohr magneton is often confused with the nuclear magneton. For us, the Bohr magneton is based on this ratio. The electron charge times h bar divided by 2 times the electron mass. Nuclear magneton for us is based on the proton mass, same formula. Nucleon states, we have basically 2 nucleons, the proton, the neutron. In our RealQM model, this 3D model, the proton is really a perfect 3-dimensional multi-axis match, I would say. We have only one single outer positive point charge shell. Neutron, we have a core shell model, a positive proton-like core, which is locked into an outer negative shell. Theoretical values of the magnetic moment, I said we have that 2 square root 2 times the nuclear magneton. I will explain this too, and then the square root 2, which is linked to the geometry of the model, really. For the neutron, we have this coherence factor, which I introduce here, times the, its ideal magnetic moment, which would be the proton magnetic moment, which yields indeed this very different value. But I said the theoretical value that we have in that third column here matches the empirically measured value which you have in the last column, plus 2.793 times the nuclear magneton and minus 1.913 the nuclear magneton. Energy conservation, really interesting, because here I come really into the math of the model. When you transition from a planar or a 2-dimensional model of oscillating charge with an irrational frequency coupling, so the ratio of omega 1 and omega 2 is 1 divided by the square root of 2, or we can write it as omega 2 is the square root of 2 times omega 1. We should apply, as we did in the electron model, the equipartition theorem to the energy equipartition theorem to sort of see if the model makes sense. Is the energy in those 2 modes of oscillation the same, 1.5 times the total energy of the thing. For the electron model, we had a 2-dimensional model, and there we basically said, okay, we have the kinetic energy, the motion of that point-like charge comes with kinetic energy, and then we have the field it generates, the electromagnetic field that keeps the motion going, and that worked out really nicely. But here we have, with a 3 model, you know, an extra element that we on which we must apply the energy equipartition theorem, and that's sort of where you know, we will have the equipartition of energy between kinetic and potential energy, between field energy and the kinetic energy of the charge. But here, in addition, we have a modal split. We're examining 2 orthogonal planes of oscillation together. They act as what is here, you know, coupled degrees of freedom. And each holds an energy associated with its specific rotational velocity profile. We get sort of what I call a quadratic conservation rule, because the modes are orthogonal components of a single bounded system rather than 2 you know, isolated particles or something. Their energies do not add up linearly. We can't say sort of the energy is equal to, you know, the energy of the first particle, if you want to call it, the first oscillation, h bar times that frequency, plus h bar times that second frequency. So 2 energies given by the Planck-Einstein relationship. We must look at a Pythagorean vector composition for the frequency and for the energy. For the frequency, we have that capitalized omega again, and Pythagorean vector composition says basically, you know, that's Pythagoras. The triangle, the hypotenusa is the square. So the squared hypotenusa is the square of the 2 sides of the triangle that connect with it, that make it up, is the omega 1 squared plus the omega 2 squared. And from there you can see that the 2 frequencies, or omega, the capitalized omega, can be written as 3 times omega 1 squared. The energy, likewise, from the Planck-Einstein relationship, we relate energy to those frequencies. So the Planck-Einstein relationship tells us that the energy is equal to, you know, h bar times the frequency. So from there you can derive, and it's a linear relationship, the total energy conservation law, which must be the energy of the proton as a whole squared, is equal to the energy in the first plane of oscillation, E1 squared, plus the energy in the second coupled oscillation, E2 squared. So you have an equipartition there, it applies, which is why we think our model really makes sense. But it doesn't really mean equal linear energy. E1 is not equal then to E2. Which also makes sense in light of the fact that we have a very specific magnetic moment, which means that you know, there's an asymmetry there. So it means that the degrees of freedom partition sort of this global invariant capital omega, such that the azimuthal or the J mode, using that imaginary unit who wants to depict a plane, handles exactly twice the structural acceleration load of the polar or I mode. That's really, again, you know, it's a lot of formulas, especially when you go from Cartesian, when you analyze that in Cartesian coordinates, which we will do in a moment. But that's the constraint you need to maintain that, you know, physical constraint of constant local velocity, VSC, across the entire sphere. Now let's come to the wave function math of this. Standard quantum mechanics really is sort of, I now think of it as sort of flat geometry or flat way of thinking about things. We have a wave function, that's Euler's function, and we can put the radius of the electron, the works, cosine, plus I, which we interpret as a rotational operator, the sine. It uses only one imaginary unit, which defines the complex plane, as you know. It's a 2D plane. And it's sort of treated as a very flat abstract grid. Standard theory basically says that, you know, we shouldn't be interpreting wave functions as something real. So it's sort of a scalar placeholder, as I would call it, that imaginary unit, while we think really of what I call a 3-dimensional operational space where things move. So the Q is there, the Quaternion, and it's really the product of well, of two of these wave functions, but really with I and J used to denote rotational operators, physical spatial operators in space and in time. It's really multi-axis rotation, mode mixing, I call it here, but the I is really a quarter turn in the XY plane, and the J is a quarter turn in the YZ plane, in the plane that is perpendicular to the XY plane. Very important to note, once you move to that sort of 3D operational space, the imaginary units are no longer like, scalar placeholders. They're non-commutative. IG, the product of those two imaginary units, defines K, and that's really the spin axis, the third axis that is there, and it's a physical spin axis. I will show that in some more visualizations in a moment. Okay, I'm back at notes that make sense here on my paper. I think, yeah, I've said that. So rotations are, yeah, we'll come to that, really composed sequentially by multiplying these two wave functions. Here we have sort of an overview. I said the math is complicated and it isn't. In standard quantum mechanics, I said a flat wave function, a wave function which is a function of x and t, but modeled really as Euler's function, the imaginary unit, times k, the linear momentum, times the x vector minus omega, this is the Breuil wavelength, times t. In 3D Quaternion math, we have this Quaternion, which evolves as a function of time, and then a product. So I would say standard mechanics really relies on sort of addition of wave functions that works really well for calculation probabilities on what I call a flat grid, two-dimensional grid. On the RealQM, we rely on multiplication to track how really a single object undergoes this synchronized rotation in 3D space. It's very important to note that because our operators, our imaginary units are non-commutative when you multiply them, the sign of rotations, and I would say of elementary wave function itself, really matters. And that's not the case in standard quantum mechanics. They say the sign is just conventional matter. And it doesn't really matter what convention you use. Clockwise or counterclockwise rotations are like just the same. You square them and you get a probability, and that's it. For us, the sign is not a conventional matter. If you go from point A to point B, let's say point +1 on the x-axis to point -1 on the x-axis, it matters if you go there through a clock-like trajectory. 2 times a rotation by I, 2 quarter turns, or if you follow a counterclockwise path, minus I, minus a quarter turn, and then another minus a quarter turn, it yields the same -1, but 2 paths are very different, and that's I wrote about that very extensively, and I complain regularly about it. So that's where the standard interpretation of the imaginary unit I in flat wave functions as sort of something that could also be minus I, and then the math doesn't change, yields the same physics. I don't think that makes sense. So the non-commutativity, sorry for my English, is essential. It's really important because if you go through the papers, you will really see also that it acts as a geometric barrier, preventing the charge from intersecting itself. And it's the only thing that really can create this deterministic, non-radiating current shell. So it's not an entirely, we don't work with sort of these abstract probability amplitudes and the density, which show a density, a probability density. The energy densities that we get from our RealQM wave function of course also yield probabilities, and in just the same way you need to square those wave functions to find to get the likelihood of actually finding the charge in some, you know, infinitesimally small or smaller subspace of that larger 3D space in which the charge is oscillating. But these amplitudes, 3D amplitudes, get a physical interpretation, as does its phase. The charge is always somewhere at some point in time. It's not like sort of a cloud-like amplitude. So let me go over it. I said that the nature of the imaginary unit, for us, it's a physical quarter-turn rotation operator in space, and we can have 3 of them. That explains Quaternion math. The physical projection, said, yeah, the standard model doesn't even do that, but yeah, you can do projections onto an abstract complex grid, and that shows you motion. The output physical interpretation is, well, there is none. It's really that abstract probability density, or the amplitude. Well, density you get from squaring the amplitude. In our model, it's really modeling motion. And so physical projections really give you envelope boundaries. Of course, you'll say, well, yeah, okay, internal quaternions, you're making it as complicated as standard or modern quantum theory. So real-world measurements, of course, are done in terms of 3D Cartesian coordinates. If you talk about motion of charge, show it. So the a unit quaternion can be split up in, or any quaternion really, into a scalar part. So the mistake here, unit quaternion can be just a quaternion. Its scalar part, just a number, which we denote as Q0 here. And its vector part, which are Q1, a scalar, multiplied by a rotation operator I, plus Q2 multiplied by rotation operator J, plus Q3 multiplied by rotation operator K, as imaginary units, you might say. So to rotate a physical position vector, the position of that charge, x, y, z, as a function of time, in that particle shell, we apply a sandwich product. You will recognize that a bit from standard quantum mechanics in 2D space. We use the quaternion and its conjugate, with 3D, but in 3D. So we get a radius, a vector, outer shell, which is equal to that quaternion times the inner radius vector times the conjugate. We can expand that into a 3x3 Cartesian projection matrix, as it's called here. I'm relying a bit on what Gemini calculated for me to show that relationship between quaternion math and the spatial coordinates of the 3D current. But that's how it looks like. You know, the R, the position vector as a function of the quaternion models, three-dimensional wave function, I would say, is basically this rather a complicated expression. But it we can substitute, and then it looks a lot nicer. We get the 4 possible combinations of omega 1 times t and omega 2 times t, cosine, sine, respectively. We can multiply that then by a sort of initial position vector. You know, we need to choose the initial state to calculate. You know, we need to know the position at some point in time in space to calculate where it's going to be next. So let's initialize it by that 1, 0, 0 vector at time 0 or at some other time. That will extract the first column of the matrix, and then you can really calculate a pretty beautiful and rather simple Cartesian coordinates. Cosinus 2 times omega 2 times, and for y you can see the formulas there. I will let you look at them for a few seconds, but as we still have 5 slides to go, and they're really important, so I hope you can hang in, because we will move away from the proton and the neutron model to modeling these multi-body problems that seem intractable. You know, the Deuteron Triton nucleus, helium, alpha particles, and we'll go to carbon, oxygen, and there's stuff in between which I will show you. So just very quickly, in the formulas you're gonna see here, I won't be too long, you can read that. So you always see sort of that square root 2 and 2 times square root 2. That really emerges from these rotational vectors in the vector equation. So the origin is really vector addition of orthogonal axes, the Pythagoras theorem, let's say. Again, yeah, 3D phase compensated flow, as I call it, for a proton, it requires simultaneously superimposing this polar rotation marked by the phase theta and an azimuthal circulation, for which we write the phase as what's the Greek letter there again? Theta and sorry, I'm a bit tired. Yeah, we'll come back. In any case, combining two orthogonal rotational models yields that vector magnitude. The absolute value of I, a sort of a rotational vector operator, and J, so vectors themselves, is square root 2. The 2 factor comes really when you transition from the flat planar projection to full spherical circulation, which again introduces this geometric factor of 4, and that's where then it appears in that proton magnetic moment, 2 times square root the nuclear magneton. The 3 and square root 3 are really with the space dimensionality, spatial degrees of freedom, with 3 spatial dimensions, and that's sort of where the squared velocity expands to 3 times their square, omega square. So that's really all about enforcing that RealQM constraint that the local charge, this naked charge, must have a velocity that equals the speed of light. And then the 4 and 1 over 4 factors that you see in the radius formula is indeed the radius scaling, spherical structural scaling. When you go from a 2D current loop, you go to a 3D shell. Distribution of the self energy, we can calculate that over a volume, will alter the effective radius, the effective charge radius. So that's where we have that 4 factor in the formula of the proton. We have inverse scaling for the energy formula. That also comes from the Planck-Einstein and mass-energy equivalence relationships. The 1 over 2 factor, you see, that's really that fermionic partition, fermionic because they can't overlap, but it's energy and action sharing, I would say, between the 2 oscillatory modes. Also the balance between potential field stress or field energy and the kinetic energy of the circulating charge. So that's where you have that total rest mass being split evenly, and you have that 1 over 2 factor. The genesis of binding. Now, we're at 1 hour, but now actually the most interesting part comes. So we have a proton and a neutron. When you put these together, you get Deuteron, right? That's where we modeled a Deuteron structure. It's really a mathematical model. This is just a visual of it, and it makes sense. We have a proton on top, and proton loop, sort of to say, with a net charge of +1, plus the electron charge, but in its proton manifestation, I would say. And then we have the neutron underneath it, where indeed you have these we have that shell model with a negative charge on the outside, a negatively charged shell, a negative charge rotating, and positive charge rotating inside of it. What happens is when these two come together, and that's why they are stable, they sort of lock their phase. It's what's called coaxial electromagnetic phase locking, because indeed locking implies that they share their spin axis. Triton, when we add another neutron, becomes really interesting. The proton is sort of the sandwich that you see there on the right hand side. Proton in the middle, 2 neutrons on the outside. They also lock, and they lock coaxially. It's sort of a calculation there of that coaxial binding potential, where you know, it really goes to 0 when the distance becomes too large, which is kind of normal. When they come together, they lower the joint energy, the total energy, and that's that negative binding energy that you get. I refer to the papers of our Deuteron and Triton models to do the calculations, and they really yield that binding energy that we find. So our geometry, our 3D geometry that we have here is, I'm really proud of that. It's sort of a multi-body problem, and I thought I would never be able to solve it. You know, 3-body problems are really difficult, even in classical mechanics, where we're just modeling, let's say, a gravitational attraction between 3 bodies. Analytically, you can't really solve it. We did solve it here, these models, by numerical analysis as well. There's no real and analytical solution. We had an optimization model, but it's fine. It's all mutually consistent, and it's all derived from first principles. So what's unique, really, and I want to stress that again, is that, you know, in mainstream physics they have this short-range strong force and an accompanying nuclear potential, which is known as better known as the Yukawa potential, to explain why the nucleons, the proton and neutron, are sort of glued together, and that then leads to, you know, gluons and quark theory. In our model, the binding is really driven by very raw, classical, mutual magnetic inductance between those current loops. So the glue between protons in our multi-nucleon models will really be those neutrons. So here we have Deuteron and Triton, 1 proton only, and then 1 neutron combining with another neutron. But in the model where we add protons, we will show it actually, we sort of drop them into that space that we have here. They will also phase lock, and so we'll really have a very nice algorithm to calculate the values, the internucleon distance, this mutual magnetic inductance, and based on that, you know, the binding energy between those nucleons. So just think about that here, the proton near field, I would say, because there is a near field, I said does radiate energy, but it sort of iron locks really the neutron's phase drift, which is why the neutron and the whole Deuteron nucleus is stable. And again, we calculated the binding energy, and okay, let's be honest, they match empirical values within 0.3%. We can tune further. I said these are a lot of integrals that we solve numerically, so you know, if we would refine the iterations, but that takes more calculation time, I'm sure we'd get the perfect value. For the Triton, again, we have a central proton ring here, which is sort of held between these 2 flanking neutron shells. This is really nice. On the bottom side, you see the first thing. We on these, based on call these coaxial models, we arranged the alpha particle into a 3-dimensional tetrahedron. You see that on the bottom. We have 2 protons, and we have 2 neutrons. Because, you know, an alpha particle is really nothing but a helium-4 nucleus. Again, we've got a paper on that. It's sort of the building block for more complicated nucleons, and these are two rather nice ones that have very nice geometrical shapes. But we also did it for lithium, for boron-11, for nitrogen-15, where the model works. Faces lock into each other, but the geometry is a bit more complicated than what you see here for the carbon, which forms basically an equilateral triangle, as you can see, with 3 alpha particles arranged in triangle-like structure, alpha 0, alpha 1, alpha 2, or we could call it alpha 1, alpha 2, or alpha 3. Three alphas, and again, these are dynamic models. This is not static, and it's really the dynamics that generate the binding energy, the electromagnetic binding between dipole fields, actually. Electromagnetic dipole fields. No need for a strong force. This model works and generates all the observed properties of the C12 model, including its symmetries, magnetic moment, etc. For oxygen, oxygen is one of these very first magic numbers, oxygen 16, 2, 4, 8, 16. Yeah, I really have that tetrahedrons within a tetrahedron, a tetrahedral packing of 4 alphas. You can zoom in on it. Again, sort of, this is not just mere, visualization. I will upload the Python code which I used to upload to create all these visuals onto my GitHub site, where you can find all Python code which I use for my papers and my generators and my stabilizers and calibrators and scanning engines. So this is not hocus pocus. Yeah, when nucleon loops relax, I can say, then they break this rigid symmetry, I would say, and then it's been out of control. But yeah, these dynamic phase-locked currents that you see here actually create, especially for oxygen, this massive binding energy, which is purely magnetic in nature. So I told you I've did, and I'm gonna go that I sort of build what I call a nuclear engine. It's a bit of a nuclear stability or stability mapper, as I call my files, as nuclear stability mapper, where we sort of gradually, really, iteration by iteration, we drop another proton or we drop another neutron in our models, and then it's really takes a lot of computing time. It's really blind initialization. That's why I call it sort of a random liquid drop sphere, a three-dimensional space of femtometer within femtometer order of magnitude, and we calculate how these current loops stabilize, and then we when they reach a stable state, we look at the structure, and we get those really nice convergence, and these are really the ground states, which we call a multi. In this case here, it's for oxygen, a multi-alpha matrix with the right binding energies based on the magnetic energy between these nucleons. So I will wrap up. I'm 1 hour 10. So this is sort of what I, I said there's papers where I optimize like nucleus per nucleus, going from, Deuteron to tritium, then to the lithium, boron, nitrogen, oxygen. But I sort of wanted to recreate also as a sort of a counterfactual, an algorithm that really creates this, what is known as the valley of stability. You see that in the, this is something, and I took from the web. I think it's from the Cambridge Dictionary of Physics or something. These blue stable isotopes and then unstable isotopes in various colors, depending whether, what kind of semi-stability or instability it is. Is the lifetime measured in years and months, in days, in hours, in seconds, milliseconds? It was successful and not successful. I think of it as a qualitative triumph. I'll explain the results, and that's what you see on the right-hand side. This stability heat map, which is based on that scanner I said, where we drop a proton or a neutron and see if it is stable or not stable, if the engine can find stability or not. The interesting thing is that you know, in the very first versions, you know, the algorithm basically crashes when it reaches sort of an instability condition. It's like a bit of a black hole, or these heat flares, these X's. So we have a machine that, or an engine code that, you know, recognizes like this is not going anywhere. We get unrealistic or unphysical values, and then it basically reports the specific nucleon as being unstable. We only, well, let me first sort of its qualitative triumph. We do have, it's not so obvious, because we only did, well, only 135 Nuclides, different combinations of protons and neutrons. The Z number went from 1 to 11, number of protons, and then sort of the total mass number from Z to about 3Z, well, to exactly 3Z actually. We could have gone wider, which is actually what you see on the left-hand figure with the empirical measurements, but you know, as I'll explain, the calculation just of this thing kept my laptop busy for more than 10 hours. It's a simple laptop, but you know, an i5 with 2 cores. But yeah, I will explain how we want to optimize that computational roadmap ahead. So the scanner did generate in this limited area of exploration of basically very light nuclei the stability value. It was pretty high sensitivity, a 94.7 recall, which basically meant that 18 out of 19 experimentally stable isotopes were effectively identified. It was an overbinding challenge. That's another reason why I sort of stopped after the machine, my laptop ran for like half a day. The heavy neutron, very, very heavy neutron-rich nuclei exhibit overbounding. We get theoretical values for the binding energy that are way above the empirically measured values. Where I said that that's a quantitative error in the model, for which there are suggestions to correct it, and they're not sort of fitting of parameters or you know, another degree of freedom that doesn't have any physical basis, but it just requires a lot more computing time. I mentioned it here, the open science blueprint of this whole thing. All of my code and my data sets, they're open source. They're on GitHub. You can reproduce the results. I mentioned the link there, github.com/Jean Louis Van Belle. I think we're there. Yeah, slide 18. I'm proud of this because I said this is these are calculations from first principles. They yield very nice theoretical results that are aligned with, you know, empirical. They are real models of you know, very complicated electromagnetic structures, which is what nucleons are. Rather than relying on, you know, Deus ex machina concepts, so as a short range nuclear force. It's really just electromagnetics, the Planck-Einstein energy mass equivalence relationship, and especially the Planck-Einstein quantization law. So again, yeah, maybe just I said, yeah, we'll talk about computational roadmap. You have iterations within iterations, a lot of degrees of freedom, especially when you arrive at sort of oxygen-like or carbon-like structures. You know, you've got like 32 degrees of freedom, or it's not parameters, but variables that you have there. The distances between those nucleons, and the iterations really started taking like 15 minutes or so. I said we used an old laptop, a Dell with an i5 processor from 2009. It only has 2 cores, but even if I would have more cores, you know, I would need to optimize the algorithm to do more parallel processing, because the calculations for each nucleon are actually independent. So we could imagine a computational structure where we calculate nucleons in parallel. But yes, processing time, as I said, it started increasing exponentially. I stopped when iteration started taking like 15 minutes. So processing heavier nucleons with this engine would require days, probably weeks of machine time on my laptop. And that's sort of where I'm thinking of, parallelization, more cores, separate calculation, and I'm thinking of sort of doing that based on the cloud, because I can't buy a supercomputer to put in my house. So that would be our next immediate technical milestone, and that's it. I really thank you for listening. I hope you stay till the end. We're at 1 hour 15 now. I wish you a great day. I will remain silent for a while working on sort of the next leap. The challenge now is really computation. The model is there and it works, and the physics are explained to a large extent. But yes, we need to get that the whole scan, including heavier nucleons, to prove that our RealQM model is really reliable. Said 94.7% recall rate is great, but we wanna get 100%. Thank you and have a great day.